Hey guys, it's Miss Aguilar once again, and we are doing part 8. I know in my last video I said that I was going to start off on the electrostatics problems, but then I forgot I had number 16. So this is problem 16, and it's going to be definitely something that you're going to see on your final exam, and how you're going to fill it out, I'll have to figure it out. I really want to make this a part of your final because I know you all did so well on these LOL diagrams, so I definitely want to make that part of the final. Okay, so again, this is number 16. Jovian is sitting in a moving car that rolls up a hill until it stops. Make a LOL diagram for a system that consists of the car, the road, and the earth. Assume that the engine is turned off, the car is in neutral, and there is no friction. Okay, all that information that was just given to us is very useful information. So let's just start off with what we know. We know that our system is going to consist of the car, the road, and the earth. So let's fill that into our, I'm trying to make this closer. Let's fill that into our system flow. So we have the car, the earth, and the road. That's a part of our system, right? Yep, the car, the road, and the earth. A little bit out of order, but it's all still there. Wouldn't be something I would ever mark you guys down for, but there you go. Okay, so we know that there's no friction. So that's the first thing we can think about eliminating is dispersed energy. So we're not going to have any dispersed energy. It starts off by rolling up, so it's moving when it starts and it stops when it's finished. So velocity final, velocity initial. Velocity initial is right here, a velocity in the position A. Remember, we do one side for position A and one side for position B, and this is cut up in position A and position B. So for position A, it says that the velocity is greater than 0. That means it's moving. That means we have kinetic energy. We can say that for sure. Do we have elastic potential energy? No, because there's no elastic springs or anything like that. And we have no height because Y is height, right? And it says here that in position A, the height is 0. So we can say we have no gravitational potential energy. So for position A, all of our energy is in kinetic energy. So therefore, we can put all of our boxes of energy under kinetic energy. So how many boxes? We're going to do 5. Now remember, this doesn't have to be perfect, but it should definitely show 5 boxes that are pretty much the same size and all stacked on top of each other. And trust me, that's not easy to do with this stylus. So okay, here we go. So we have position A, all kinetic energy. Position B, do we have any velocity? Well, velocity in position B is equal to 0, so we can get rid of kinetic energy. And remember, it's stopped. That's what we said at the beginning. So it's not moving. Is there elastic potential energy? No, it hasn't like hit a spring or anything. Is there height? Yes, there's height. It's greater than 0. And I mean, just look, it started at this level and it finished up here. So there's definitely height. So all of our energy in position B is going to be in gravitational potential energy. So again, we can put 5 of our boxes, energy bricks, here. That's 2, that's 3, that's 4, and that's 5. Sorry, they're not super perfect, but I try. Okay, there we go. What's the last part? Qualitative energy conservation equation. So what does that mean? Conservation of energy just means that whatever you start with, the total amount will be equal to the total amount of what you end with. Well, how would we figure that out? How much energy we have in the beginning and how much we have in the end? We would take the equation for kinetic energy, and if we knew any of these values, we could plug those in. That is our position A. Our final energy is gravitational potential energy, so then we would figure that out by putting values in that we knew and calculating the total amount of energy to start and the total amount of energy to end with. Now remember, you could solve for just one side because whatever that side is, it's equal to the other side. All right. Now, what if we had like all these other types of energy here? Well, if we had like, let's say dispersed energy, let's say the question was that there was actual friction. So there is friction, then we would end up eliminating one of these boxes here, right? And we would end up putting a box in dispersed energy. So if that was the case, we would end up having to add dispersed energy over here. Okay? Of course, I won't have you guys doing that because this is probably going to be like the question that's on the test. Just something to think about. Okay? All right, let me pick up on this next one, and we're starting with electrostatics. So that was the end, that last LOL diagram. The last problem, the LOL diagram, was energy, work, and power, and now this is electrostatics. Don't forget, waves is not a part of your final study guide. That's because I have you guys using your study guide from Unit 8, the one I handed back on Thursday and Friday. If you were not here on either of those days and you didn't receive your study guide, then come see me on Monday and I'll be sure to hand it back. If you don't have it and you were here on those days, it's probably because you didn't turn it in or you didn't put your name on it, and I have a whole pile of no names. So make sure you guys check those out because I can't give any credit after Tuesday. Okay, how are gravitational electric forces similar and different? And which has a stronger force, or which force is stronger? Well, gravity attracts only, right? It pulls us down to the center of the earth. Where electric forces, EF, I'm going to call it because it's just easier, does both. Attracts and repels. So how are they similar? They both attract. How are they different? Different. Electric forces will also repel. Okay? Which force is stronger? Well, we figured this out when we were doing our jigsaw, electrostatics jigsaw activity. Remember, I had you guys starting in 3 groups. Then I had you split off in different groups with the colored papers and then come back together to your home groups and fill in that white paper. These questions come from that activity. Which has a stronger force? Well, electric force is stronger. Actually, almost 1 billion times stronger than gravity. All right. Let's go on to the next one. What is the fundamental rule that governs the behavior of all electrical phenomena? Well, this one is easy because this is what we talk about all the time, right? Positives and positives will repel. Negative and negative will repel. But opposites will attract. Now, how do I say this? Like, repel, opposites, opposite, attract. Sorry, I ran a space there. All right, that's the fundamental rule. What 3 types of particles form the building blocks of all atoms? We have 3 types. Let me change my pen size. We have protons. We have neutrons. And we have electrons. Where are they in the atom? Well, the protons are in the nucleus. And their charge is positive. Neutrons are also in the nucleus, and they are a 0 charge, they're neutral. And electrons are on the outside of the nucleus, and they have a negative charge. Draw an accurate image of a helium atom and include the electrons, proton, and neutrons. This should say an S there. There's not just one proton. Okay, well, the center is, let's do the protons in purple, P, purple. So there's 2 protons. 1, 2, of course, this is not to scale. We have a neutron, which is a 0 charge, in the nucleus. Let's call this the nucleus right here. And then we have electrons, electric. Let's do red. We have the outer shell. This is the shell outside of the nucleus. And when you guys start taking chemistry, and actually even in biology, you'll talk about this, there's a whole bunch of different layers or shells, we call them. And the valence shell is the outermost shell. And any atom can have a number of different shells depending on the amount of electrons you have. If you have like 80 electrons, you can't put all 80 in one shell, and it adjusts as you move up, and you can only put a certain amount of electrons in each shell. The first shell, the shell closest to the nucleus, can only house 2 electrons. Okay. Oh no, I erased the whole thing. It can only house 2 electrons. One here and one here. There you go. That's a helium atom. He. Helium. Helium is one of those stable gases. It's never going to seek out an electron or, give up an electron because it is satisfied. The only number of electrons that can be in this outer shell are 2. You can't add more to it. So the only reason why certain elements are going to take electrons or give up electrons is because their outermost shell isn't full or, can get rid of one extra one. I'm going to stop there, you guys, and I'm going to start the next video because, again, I'm trying to keep these under 10 minutes, and I think I might be a little bit over. But, all right, I'll see you in the next video.